Back again with the next problem, problem number 3. What I did not realize is that this cheapo demo program thingy only allows me 10 minutes of recording time, but that's okay, I can splice it together later. Alright, so this next question is, when is the energy crossing the boundaries of a closed system heat, and when is it work? Well, since we already talked about the piston cylinder system, let's just keep using that. Okay. Now you remember when I said when the piston is moving up and down, it's transferring work, and when it's sending heat out into the surroundings, that is heat, of course. When it's sending energy out into the surroundings, that's heat. Okay, but we need a little stricter definition than this is heat because it's red and that's work because it's blue. Okay. So the explanation that Professor Moore gave was that heat is the energy transferred due to a difference in temperature. Okay, so if we have a piston system where the T outside is equal to the T inside, the temperature, that is, we have no heat energy crossing this boundary. It's just not happening. Which means all the energy that crosses this boundary must be work. And that's honestly as simple as it is. If it's anything, if you have a closed system, what is defined as a closed system, if you know it's a closed system, and the temperature inside the system and outside the system are exactly the same and there's nothing being transferred, from what I understand, for our explanation anyways, that then everything, all the energy that comes out of that must be work. Most of the time you have friction, so even if the initial temperature inside and the initial temperature outside are the same, the movement up and down will produce a heat and will produce a temperature difference, and then there will be a heat energy transfer. But assuming it's a perfect system with perfect slippery sides and whatever, if the temperature inside and the temperature outside are not the same, there is no heat transfer. All the energy is transferred through work. Okay, I feel like this particular problem is just going to be really, really, really redundant because I really like the way that the professor explained it in whichever lecture it was that we had this particular question. And so I'm just totally going to do it the way she did it. Okay, so imagine that you have a tank. Okay? And this tank is full of some stuff, some fluid with all of the typical fluid properties. Oh, hold on a second while I get the right notes for this. Oh, stop. There we go. So the properties that Professor Moore considered worthwhile in mentioning, don't know what I should be calling her, professor, doctor, whatever. I'm just going to keep calling professor because that's pretty safe, because I don't want to give her any borrowed feathers. Anyways, so it has property of mass, that is a lovely M, volume, temperature, pressure, and density. Okay, so now let's imagine that we're not changing anything except we're splitting this down the middle. We're not shoving all the mass onto one side, we're not doing anything like that. This is a gas or maybe a liquid, it's some sort of fluid, and we're just going to stick just some wall right in the middle of the box, like a magician sawing someone in half. Let's just, except with a, anyways, yeah, so we're putting a wall right down the middle. And we're going to look at only one side of the wall. This wall is not permeable, which means that things are not going to be transferring back and forth. So all the properties are just as they are now. Okay, so this is 1/2 of the mass. Makes sense, right? I'm assuming there's no great pressure difference in the box to start with. No. The volume is 1/2 of what it originally was. That's the definition of splitting a box in half. You're dividing the volume in half. The temperature is still the same as it once was. You know, I'm assuming this box has pretty homogeneous properties. So the temperature is still the same. Alright, the pressure is also the same. Even if this is a liquid, where there's a linear increase in pressure, it's still the same linear increase in pressure as it would have been if the box was twice as big, like it was before. Density, of course, is still the same. If the pressure is still the same, then for any gas, you know, well, I know there's the whole ideal gas law. Okay, so let's not even go there. Let's pretend I didn't say that. The density is the same because we're assuming this is a homogeneous box. Alright, so intensive, or intrinsic, or, you know, inherent. They all mean pretty much the same thing, which is that it is a property that is little dependent on the circumstances exactly. Well, that's probably not a good description, but in this case, it means the things that didn't change when we stuck the wall in. Okay, so that would be these properties. These would be the intensive properties because they were not affected by the change in volume. The mass and the volume were, however, changed. Oh yeah, that's how rho wasn't changed because we had 1/2 mass and 1/2 volume. The mass to volume ratio did not change at all, so of course rho stays constant. That would have been a better explanation. Anyways, so these are extensive properties and these are intensive properties. Okay, so these did not change, or these did change with a change in volume. These did not change with a change in volume. So there's your answer.